So far, we have studied about modulation and signal beating, but the question to us is, how do I find out this modulated signal which has been carried by a carrier signal. Now, we talked about amplitude modulated signal, how carrier frequency carries a modulated frequency. The information from the machinery to us is actually the modulated signal. So, when you looked at the amplitude modulated signal in time domain, we had a signal of this nature, wherein this is the high frequency carrier signal. Okay. This may not be of interest to us, but it is this envelope. If we look at this envelope, which is a low frequency signal, as you can see from the time period. Is actually the signal which contains information, which will be useful for machinery diagnostics. The question before us is, if we go to a real machinery, we will be having such signals. On top of it, there will be a lot of noise. So, question is, once I do an FFT of such a signal, which has the high frequency signal, which has the noise, etc., in the frequency spectrum, the significance of this green signal in our case will be lost. It will be kind of buried in a high frequency noise. Okay. There will be a lot of high frequency noise, and then how do I identify this? Or well, intuitively you can right away say, no, why don't we filter it? We will filter the high frequency signals, so that the green signals, the low frequency green signals are available. That is fine. It is, people can do it that way, and people also do that way, that putting a high pass filter, where they will rather a low pass filter, wherein they will remove certain high frequency components and look into the low frequency signal. But sometimes it happens that even in these low frequencies, there is a lot of noise or other phenomena happening, which kind of obscures this green signal. So, we have to find out ways to find out this low frequency envelope. So, this happens because of signal modulation. So, at the generation point of the signal, there is a modulation effect happening because of the frequency of one being related to other, or one being caused by the other, like the case of the rotating fans which I was telling you about. So, our signal has got modulated, it has come to us as a modulated signal. So, our objective now is to demodulate the signal. So, this demodulation has to be done by one is, I can put a set of low pass filters, and then there are another technique which we will be covering mostly today, is this Hilbert transform. But the problem with low pass filter, as you will realize, is we do not know the frequency content of the signal. So, what will be my cutoff frequency of the low pass filter is a very difficult thing to establish. But diagnosticians or analysts who deal with certain signals, they play around with the low pass frequency, the cutoff frequency of the low pass filter, and see whether any meaningful information is being obtained in the low pass low side of the frequency spectrum. That is one way, wherein just by analog filtering we can do some sort of a demodulation. But now there are well established digital signal processing techniques using Hilbert transform, which will demodulate the signal to find out its envelope. So, envelope, which we call as envelope analysis, is nothing but it is also signal demodulation, because I need to find out the low frequency signal which is coming as an envelope. I can demodulate the measured signal, and then I can get the information about the signal. Once this signal has been demodulated or envelope analyzed, I can then do my traditional FFT to find out its frequency content. Okay. So, demodulation itself is in time domain, or the low pass filters, we set it in all the signals from these filters are again in time domain. After the Hilbert transform also the signals are in time domain. So, and after we have got this time domain signal, and that was that green envelope signal which I talked about, we can do further signal processing like an FFT analysis. Okay. Now, I will before I go to the process of doing demodulation or envelope analysis, let me give you one example as to how this modulation occurs in a real machinery, and then how we can demodulate it to find out the defect frequencies of that machinery. Let us take the case of a simple ball bearing. Okay. So, ball bearing actually has many elements. This is known as the outer race, which is usually stationary, and this is the inner race, and these are the rolling elements, and these are the balls or rollers. Okay. Now, there are possible scenarios. This is rotating, and this is usually fixed. The outer race is fixed in our case, and this is rotating. Now, there could be few possible cases that I have a defect located here in the outer race. In this case, if you will imagine, if you look at the time signal, and each time these balls, basically these balls will spin and rotate around the inner race and outer race, and they have these rotating frequencies that can be calculated from the dimensions, which we will come to later on. There are different, because if the shaft is rotating at n rpm, all this will be relative to n rpm, some will be little higher, some will be little lower, and so on. No matter what, each time this rolling element or the ball passes over the outer race defect, it is as if you are going over a pit, okay, each time. And if you measure the vibration created because of a ball hitting a pit, each time I will get an impact, and then I will get another impact, another impact. As many times the balls hit this defect, I will be getting a continuous pulse of impacts. Okay. Now, this impact, the frequency of the impact is actually inverse of this time period, and that relates to the speed at which the balls are going over the defect. Okay. but the phenomena is actually inside this impact. If you magnify one such impacts, maybe you will get a ringing signal like this. The frequency which is there or which is characteristic of this defect is actually inside this. This is one way of getting an uniform signal out of this bearing because of defect in the outer race. On the other hand, suppose the defect was there in the inner race. Let me put it here. Okay. And because the shaft carry a load and load is always acting downward, some load W. Okay. So, each time the defect comes under the load axis, there is a great amount of force on this defect here and the outer inner race, and then once the inner race moves away, this force will decrease and so on. So, the intensity of the vibration will be modulated as a function of the rotational speed, and if I was to draw it here, I will have one defect, in time domain. These high peaks mean the IR defect is right on the axis of the load on the shaft acting downwards, and of course, this is the vibration signal. So, you will see that there is again a effect of modulation occurring here. So, this is how physically a modulation also occurs. Okay. Now, if I am talking about a gearbox with intermediate shafts, you can imagine there are about 6 to 7 bearings, and you see, because if I put just one transducer on the machine, and this transducer, suppose it is to measure, I am going to explain to you the severity and the magnitude of the vibration levels and what kind of contamination a transducer may be having. Suppose this is my shaft, this is my gearbox. Okay, there are bearings here, bearings here, bearings in the holding the intermediate shaft, and there could be gears. Okay, this is my input shaft, output shaft. If I just put one transducer somewhere here, and these are all the gears, bearing B1, B2, B3, B4, B5, B6. A simple gearbox has B1 to B6 bearings, G1 to G4 gears, and I have one transducer, say T1. So, the signal measured by this transducer T1 could have everything. Okay. The problem before me is to identify from signal processing which bearing is defective, and this is what in reality we face the problem. So, the effects of, suppose there are few bearings which are which are having defect, there are a couple of gears which are having defect. So, everything is a composite signal is what we get, a sum effect of all problems are there in one signal. So, the problem before us is how do I find out which bearing is defective. So, we have to know the characteristic frequencies of each of these gears and bearings, and if specifically if I come to one bearing itself, the inner race there could be a defect, outer race there could be a defect, in the rolling elements there could be a defect. So, all these defects will have characteristic frequencies, and these frequencies we will tell later that how they can be calculated once you know the rotational speed and the dimensions and the number of rolling elements. So, if these frequencies are known to us beforehand, I am sure that in this signal these frequencies are buried, they are there, but then we have to have a right kind of eye or magnifying glass, if you may say so, to look into them and find out what these frequencies are. So, the envelope analysis is one such technique, or signal demodulation is one such technique by which I can find out these characteristic frequencies. So, nowadays in the FFT analyzers which are available, there is an option of doing FFT after envelope analysis. We do the fast Fourier transform not of the total signal, but only of the signal which is carrying the information. I am not interested to know about the carrier frequency. Okay. I am not interested to know the rotational speed. I am interested to know whether my defects which are showing as modulated signals, which are showing us that envelope, can be detected in the signal. Okay. So, envelope analysis is that way a very powerful technique for signal processing. Now, as I was telling you, filtering is one method of finding out the envelope in a signal, but the another method is this technique known as the Hilbert transform. So, before I go into Hilbert transform, I just wanted to briefly tell you about this signals which are, one is an amplitude modulated case. If I have this amplitude as a function of a cosine or a sine series, this is the frequency of modulation, and then this is the carrier frequency, you will see that the amplitude, the modulated signal can be represented as this equation, and you will see the sum and difference signals also show up, and that is what we did by what is known as the sidebands occur because of a modulated signal. Okay. And apart from the carrier frequency, but just to recall, if the signals were beating, you will not see an individual frequency, you will only see the sum and difference frequencies, but once they are modulating, you will see an individual carrier frequency and the sidebands around the carrier frequency as f c plus f m and f c minus f m. And then once you have the frequency modulated, you will see a lot of symmetrical sidebands, okay, and given by this number k here. So, f c plus k could be 1, 2, 3. So, there are a lot of symmetrical sidebands will occur, and this particularly occurs in gearboxes. We will see practical examples later on. But the question is, we know how to detect sidebands because of signal modulation, okay. But question is, if I am just interested to know f m, it becomes a problem for me, because f m could be a very low frequency signal. How do I find out that f m from a signal analysis? Okay. So, that is the problem we have in front of us. So, there is one mathematical technique which we do. For example, if the two signals are beating, I will get this kind of waveform. An amplitude modulated signal would also look like this, as you would have seen. So, this signals here are actually high frequency carrier signals, because this number of data points are 1000 here, and that the time period here could be dependent on the sampling frequency, whatever sampling frequency is taken here. So, number of data points times delta t. So, delta t will be total time period, will be, just to recollect, total time period is nothing but n times delta t, which is nothing but n times 1 by f s, n by f s. So, total time period of a block, if n is equal to 1000, f s is whatever, you will get that many seconds here. Now, the question is, I am interested to find out this envelope here. Okay. How do I do that? There is a technique which is very widely used, Hilbert transform. In this, what happens is, this is a mathematical expression of the Hilbert transform. Okay, we generate an analytical signal Z t here, which is the original signal x t plus the imaginary part is the Hilbert transform of this signal x t. Okay. So, this analytical signal, actually if you do the FFT of the envelope signal, we will get what is known the analytical signal itself is going to give you the envelope of the signal, and this can be done in the software MATLAB. If you use the function Hilbert on an amplitude modulated signal, you will get the envelope. Now, if you look here, this is the envelope which was of the beating signal, which has been obtained by just doing Hilbert transform of that beating signal, and this you all can do in software like MATLAB, etc., very easily. So, no matter what, because this is the low frequency signal which has been carried by my high frequency carriers. If you look at the high frequency carrier here, okay, this high frequency carrier is carrying this modulated signal, and I am interested to know this envelope. Okay. And I will not go into the mathematical details of this transformation, but it suffices to say just by doing Hilbert transform of the signal, you will get an analytical signal, wherein you can get the instantaneous frequency of the signal, you can get the phase angle of the signal. I will not go into details of this right now, and then we will very easily get the envelope. And this envelope can be, you can do the frequency analysis of this envelope signal, so that you can find out the properties of the signal, frequency contents of the signal. So, envelope analysis of the bearing signals can be done, and then we can get the low frequency bearing defect signals. Because if you will recollect, these bearings, are elastic members. Say, let me take the case of an outer race, just an outer race. Say, bearing is used in a machinery wherein the maximum RPM is 3000 RPM, and that boils down to 3060, that is 50 hertz. So, any operation in this bearing is going to produce a 50 hertz excitation frequency, right, or few multiples of it. At the most, maybe if it is 10 times the fundamental, this could be 500 hertz. So, the external forcing function, external forcing frequency on the bearing is about 500 hertz. Imagine, because this is an elastic material, it has its mass, it has its density, it has its stiffness, etc. Okay. So, this rings also have their natural frequency. We can model them in some equivalent stiffness and mass. Obviously, a bearing designer is not going to design a bearing whose natural frequencies are in this range. Otherwise, every time the bearing is in an operation, it will get excited at its resonance. So, no designer would do that. Usually, as a thumb rule, the natural frequencies of the structural elements of the bearings are much higher and above 20 kilohertz. Okay. So, that during the operation of a bearing, these do not get excited, the bearing does not have large motions because of its resonating conditions. But you can think of it another way. Suppose now this outer race, there is a defect, as a pit, as if you are going on a road, okay, and suddenly there is a pit. So, if these balls are traveling, spinning and traveling on this outer race, what is going to happen, that if I come across this pit on the outer race, I am going to have an impulse. This will be an impulse excitation. As if something has hit the outer race, as if you have banged on it, like you go on a bump or a pothole on the road, you feel that impulse. So, this bearing has got excited by an impulse, agreed. Now, I will draw your attention to your earlier theories on Fourier analysis. Any time domain signal A t, suppose this is a very small signal of dimension tau. If tau becomes very small, its response in the frequency domain will be very large, and you perhaps would have done this as a homework, I believe, and so on. Okay. Or if this tau tends to 0, I will have the frequency response of a similar to a broadband excitation. That means, here because of an impulse where time period is very small, the frequency response is very large. Time and frequency are inversely related. So, now if I go back to the example of my rolling element bearing, the bearing is getting excited by a frequency because of a small defect, which looks something like this or something like this, okay, almost close to an excitation where all frequencies are present. Okay. So, if this mechanical system, which has a stiffness, which has a natural frequency omega and k by m, is getting excited by a forcing function wherein all the frequencies are getting excited, obviously its natural frequency will get excited. If I was to pose the problem another way, suppose I can model the bearing by this set of equation. By a forcing vector in the right hand side. So, this force is actually this, in the frequency in this in time domain, but in the frequency domain this would look like this. That means what? The system, in this case the bearing, has got excited at all the frequencies and it has got excited at its resonant frequencies. So, I am going to have a resonant condition or it is known as the high frequency resonant technique, HFRT. So, in this case what happens, if I go to the bearing signal, on top of the amplitude modulated signal, I will have, if I was just to draw them visually, on top of it I will have also large motion. So, I have a high frequency resonant technique, a resonance phenomena occurring. On top of it I have the low frequency amplitude modulation. And my transducer is not a mathematician. Transducer cannot understand all this. Transducer will faithfully represent my mechanical vibrations as an electrical signal and it will only give me this. So, it is we through our technique we have to understand whether a resonance has occurred or whether a modulation is occurring, because in such large motions very low frequency small amplitude modulation will be obscured. On top of it there will be so much of signal noise. Okay. So, we have to again find out by what method I can be sure that defect in the bearing has occurred. So, one way is to monitor the high frequency vibrations, anything greater than 20 kilohertz. So, because of an impact or because if you say because of a shock, this is constituted as a shock. Because of a shock, large motions occur and they occur at high frequencies. So, traditionally or conventionally there are many products. One such is the shock pulse meter or SPM. This essentially means to measure the bearings response at frequencies beyond 20 kilohertz to check whether the bearings resonance has been excited or not. Well, who is exciting the bearings resonance? It is not the normal operating functionals of a bearing, but it is if there is a defect like a pit, like a defect in the inner race, outer race. Because of this pit I am getting an impulse and this impulse's frequency response is a wideband response which has excited the right hand side of the equation. So, I am getting large motions at the resonant frequencies of this bearing, and as the bearing designer they always make sure that the bearings natural frequency are not in the operating frequencies of the bearing and they are at a frequencies much higher than the operating zone and usually of the order of 20 kilohertz. So, in fact, a vibration measurement at high frequencies is a sure indicator that a defect has occurred. So, in fact, a shock pulse meter is nothing but a high frequency vibration meter. So, then we can say for sure that a frequency defect has occurred. But we have a little more diagnostic problem in the sense here. Well, this defect is because of what? Is it because of an inner race? Is it because of a ball? Is it because of an outer race? So, from the geometry if I can calculate the defect frequencies, okay, this could be because of the inner race, outer race, ball or the fundamental train frequency, and I will tell you later on how these frequencies can be calculated. Once these frequencies are calculated, we can then use the envelope analysis or signal demodulation to identify in the frequency spectrum whether these frequencies show up. Okay. And then I will when we talk about the fault diagnostics and bearings, I will give you certain actual measured values and measured spectrums of the inner rest frequency, outer rest frequency after the modulation, because if you will see, I will just I will give you two frequency spectrum, one without envelope analysis, one with envelope analysis. One without envelope analysis, okay, where this could be the defect frequencies, but if I do it with the envelope analysis, so this could be the IR defect, this is 2 times x, 3 times x and so on, and these are IR, this could be OR, and this is what without envelope, this is with envelope. These are the vibration signals. In fact, the signals which I have drawn here, they are even much I would say dirtier or noisier than this spectrum shown here. So, it becomes sometimes very difficult to know whether it is an IR signal or a noise signal. But once we do an FFT sorry envelope and then do an FFT, all these modulated frequencies will very nicely show up. But this is not to be confused with the shock pulse meter, because shock pulse meter is a very high frequency vibration measurements, which will only tell you about the level. But with this envelope analysis, I can find out the individual defect frequencies. Okay. Now, I will give you another example here, as to you must have all realized. This is from a plant very close to Kharagpur, wherein this is a electrical motor. It is a 3-phase electrical motor, and then there is a blower. Basically, they take in air and from the atmosphere, and there are series of blowers in this blower house. There are about 5 such blowers, and each one operating at close to 2900 RPM. And then you will see all of this, there are a lot of valves here, because these 5 blowers are in series, and eventually they will take in the air and feed to the excuse me feed to the blast furnace. Okay. Now, in this single room, because there are 5 blowers, what happens if one of them is running at a frequency or a speed little less than even 1 RPM or on a few RPMs, the frequency of these machines will be different, and because they are close by, you will the phenomenon of beating is going to occur. And if you enter such a place, you will hear this kind of a loud decreasing increasing sound. If you go to any plant wherein many machines are supposed to operate at the same speeds, because of some reason or the other, if some machine is running at a little lower speed than the other, you will hear this kind of wow, this kind of waning waxing noise, which happens even in the ship engine rooms also, I believe, because there will be machines which will be running not exactly at the same frequencies, and this happens in the blowers also, of course. Now, the reason I wanted to show you this is, this sometimes should not be confused as modulation, okay, because if you look at the response of a beating signal and a modulated signal, they all look very similar in the time domain. But if you look at the frequency contents of these rooms of these signals, they are quite different. In the amplitude modulated signals, I will see side bands FM, FC plus minus FM, and also if I am interested to know FM, I can do the signal demodulation or do the envelope analysis. But if I want to find out the two frequencies which are responsible for beating, I can simply do a fast Fourier transform, wherein I have to be sure that the delta f is very fine excuse me, very fine. Okay. To distinguish beating, I need to have a frequency resolution where delta f has to be very fine. Suppose I have one signal at, so this is 10 hertz and this is 10.5 hertz. If my delta f is 2 hertz, I am never able to distinguish between these two signals, isn't it? But these signals would have created beating. So, in my frequency domain, I can very easily miss this if delta f is kept at 2 hertz. If delta f was equal to or less than 0.5 hertz, I will be able to distinguish them. So, that is the problem while doing frequency analysis, to identify beating. Otherwise, I will just miss this, and beating is because of independent frequencies. Because in this example, these two blowers or two motors may not be having the same speed, okay, and they are independent. One is not related to the other, okay, but then this will give rise to a beating phenomenon, as opposed to the case of the ball bearing, wherein the defects and the frequencies which are related, because if I have the inner race rotating at one speed, the outer race, the balls, their frequencies are all related to the inner race frequencies, okay, and thus they modulate because of the load, modulate because of the speed, and so on. So, amplitude modulation can be very nicely, because if I have an FFT of a signal wherein there is a modulated frequency of a very low frequency FM, this will be, as I was telling you, very easily obscured in other noises. So, envelope analysis is a excellent method to find out FM, okay. But there may not be any other frequencies next to FM. If I have finer resolutions, I can check that, but if I see other two frequencies 10.5 and 10 who are not related to each other, then I can say the signals are independent and they are responsible for beating of the signal. Okay. Now, in a plant like this, I should just mention it to you that in fact, we at IIT Kharagpur had designed this enclosure for them just to kill this noise which was generated because of the beating. Because again, if you see, if I have one machine generating 100 decibel of noise, another machine of course another 100 decibel of noise, the sum effect will be 106 decibels, but because of beating at some frequencies there will be a large amplitude and that amplitude will be very loud. So, to reduce that we can put an enclosure wherein you can put in lot of lining material. We will come to this later on, but I will just show you another spectrum of this noise which was measured by the which was measured and then we had analyzed this at that frequency. Now, this what is here is a 1/3 octave spectrum. We had talked about the different types of filter, wherein I can have a fixed resolution filter, wherein if a filter has an upper band and a lower band, okay, the bandwidth of the filter is upper band minus lower band. In the fixed resolution, case like we do in the narrow band when you do the narrow band analysis, what happens is delta f, we specify delta f. How do you specify? It is 1 by t, it is 1 by n delta t, it is equal to f s by n, and that is fixed when we do the narrow band FFT analysis. But if FFT analysis was not done, but I am doing a frequency domain analysis by filtering, I can set filters of different bandwidth, I can set filters of constant bandwidth, or another filter is percentage bandwidth. In percentage bandwidth, there is a relationship between this upper frequency and lower frequency. If the upper frequency is equal to twice of the lower frequency, this is what is known as an octave band. And if the upper frequency is 2 to the power 1 by 3 FL, this is a 1/3 octave band. Okay. The reason we have octave band and 1/3 octave band, there is a history behind it, because our human ears can distinguish octaves of frequency very easily. My ear may not be able to distinguish 10 hertz and 10.5 hertz. I may require a narrow band analyzer to distinguish between 10 and 10.5 hertz or 10 and 10.25 hertz. But perhaps our human ear, some of you can perhaps distinguish between 100 hertz or 200 hertz or 400 hertz, 1000 hertz, because they are almost multiples. So, traditionally when FFT analysis was not being used, people were using fixed band filters, analog filters to do filtering, and nowadays also, since this has been predominantly used in the industry, people stick to what is known as 1/3 octave band. And if you look at this spectrum here, this closely corresponds to about 500, 600 some odd frequency, which happens in this band. You will see all the levels are pretty low, but it sticks up around 6. If this is 400, this is 1 kilohertz, there is a 1/3 octave spectrum. So, there is a percentage bandwidth here. Around this is nothing but the electrical motors blade pass frequency, because behind the electrical motor, such large motors, traditionally each of these motors was close to about 900 kilowatt was the power. Okay. And this large motors, okay, and then the shaft which is rotating, and this motors and running continuously, and then they are all blowing in hot air. This air finally goes to the furnace, okay, at a very high flow rate. So, these motors and all become heated up. So, in fact, at the rear of the motor there is a blower, and this blower has a fan. Okay, and this fan, there are number of, I think about 23 vanes. So, this air gets sucked into the motor, and this motor is getting cooled, and this vane creates, because it is a fan rotating at very high speed. This is what is responsible for the motor noise, and this frequency has shown up here. And if there are 5 such motors in that plant, and there is a small variation in their speed, this is giving rise to beating. Okay. And obviously, I cannot bring down the beating phenomena, because for operational reasons some of the fans rotate at slightly lesser speed than the other one. So, all I can do is to reduce the effect of the large noise which is heard because of the beating, is to put an enclosure on the motor. Of course, there are other issues that this enclosure should not introduce, should not increase the temperature inside the motor, because the bearings which are there, they are certain class, they should not get overheated more than 75 degrees Celsius, because if you enclose it, the cooling air capacity to the motor reduces and the bearings become hot. So, bearings may seize. So, they are all, it is like a domino effect. So, any plant, if you see, there are enough protections for the motor, for the bearing, for the vibration, for the noise. Particularly for the bearing, we need to also have a round the clock temperature indicators to see whether the temperature is increasing or decreasing or staying still. If the temperature increases, we need to take precautions as to how to reduce the bearing temperature. Maybe we should have chillers on the enclosures when we have a hot environment wherein the machines machines will get heated up because of an enclosure. We need to have chilled cool air going in, okay, like an air conditioner, small air conditioner put. In fact, such enclosures are there, enclosures with having chillers in them. So, the temperature does not increase. Okay. So, the purpose of this lecture was to demonstrate to you the two phenomena which occurs in machinery. One is beating as occurred in this case of the blower, and other is signal modulation. These are two phenomena which occur, and then we have to find out methods how to distinguish them. To distinguish beating, I have to have the frequency resolution reduced. To distinguish amplitude modulation, I have to do what is known as the envelope analysis. Envelope analysis could be done by low pass filtering, or it can be done by Hilbert transform. Okay. And once we have understood the signals, we can now diagnose the fault in the machine. Okay. Thank you.